My name is my name is Teh Chiyuan. My car metric number is 221011145. Now I will be introducing the importance of adaptive protection in modern power system. First of all, power system protection is crucial to maintaining a stable and reliable electricity supply. Traditionally, this was done using the device like electromechanical or static relays. Their system operate based on fixed setting designed for fault conditions that are already known. However, our modern power grids are no longer that simple. With the rise of distributed energy resources like solar panels, batteries, and electric vehicles, the grid has become more unpredictable. Power can flow in multiple directions and conditions change rapidly. The problem is traditional protection method cannot keep up. They were built for one directional stable power flow, so now with all their dynamic changes, fixed setting may cause delay in tripping or even worse, fail to respond at all. This opens the door for new, smarter protection approaches, and that's where adaptive protection system come in. Well, I will explain the further in the next slide. So let's look at the core problem. In modern smart grids, especially those with high DER penetration, the grid behavior become much more dynamic. The direction and strength of power flow can change suddenly, like when a solar panel drops output or an EV starts charging. Traditional relay cannot adapt to their changes. They are set with fixed parameters and they are expect predictable conditions. So when something unusual happens like a reverse current or low fault current, they may misoperate. That means unnecessary tripping, blackouts, and even safety risks. To fix this, frequent relay updates would be needed, but that's just not practical in real time. It would take too long and require too much manual work. That's why this project focuses on adaptive protection, a smarter, flexible approach that updates relay setting in real time. The goal is to improve the reliability of the grid, especially in smart environments, and ensure that protection stay effective no matter how the system changes. Thank you.
My name is Anura Analaki Jongjut and my matrix number is 221091035. Now I'm going to explain about the methodology of our project. Okay, this is our flowchart. So as we can see here, first thing is start. Then after that we start to measure. After measure, then we can detect the fault. After that, the open feeder circuit breaker will open. So when the fault detect and open feeder circuit breaker do not open, so it will come back to the measurement. So if it can operate, so the next step is will be fault clearance. So this fault clearance will clear those fault that had been detected. So if yes, so it come back to the measurement, so the process will be repeated. When the fault clearance is not available, so the we should do the microgrid shutdown. Then next we'll proceed to the fault elimination, then reconnection process and end. So this is the roughly our main flowchart for this title. Okay, next is the method for adaptive power protection. So first thing is system analysis. So as we can know, there are basic types of power system, which is transmission line, generator, load, transformer, and distributed energy resources. So there are many types of fault that can happen in power system or in transmission line. So first is single line to ground, second is line to line, then the third is line to ground. So based on this analysis, the short circuit currents and power flow behavior is under varying load and generation condition using the standard calculation formula. Okay, next is the protection principles. So by theoretical technique, there's a four protection principle, which is time grading, current grading, zone-based protection layers, and also lastly overcurrent protection, distance protection, and directional release protection. So next is development of adaptive protection. So what is adaptive protection? Means the ability of the release to modify setting based on the changes of network to clear the faults that occur. So there are three types of the adaptive parameter. First is time release, second is directional sensitivity, and third is the current thresholds. Okay, next will be fault case assessment. So what is fault case assessment? Fault case assessment is the setting of adaptive protection that should be adjusted to ensure there's better selectivity and faster fault clearance, so it won't delay the system operation. So next will be the basic setting may fail to clear the under high voltage fault in power system, especially related to those high voltage. Okay, lastly is the performance and evaluation criteria. So there are four types of indicator. A is selectivity, B is reliability, C is fault clearing time, and lastly is sensitivity.
My name is Nesh Anlaki Magindran and I will be presenting about results and discussion. So the figure shows network diagram of the adaptive protection system. So real-time adjustment of relay settings. Adaptive protection systems continuously monitor the operating condition of the network. Example, power flow, DG availability, grid and islanded mode. Based on these conditions, they dynamically adjust TMS, which is time multiplier settings, pickup current, tripping time, and this ensures selectively fast and reliable fault isolation, avoiding unnecessary outages or delays. So the second point is impact of operating modes. Two key operating modes were analyzed, which is grid connected mode, system connected to the main grid with or without active DGs, and islanded mode, system isolated from the grid, supplied entirely by local DGs. So in islanded mode, the system becomes more vulnerable due to reduced fault current levels. The first one, conventional protection failed to maintain coordination. Adaptive protection dynamically recalibrated relay settings to suit the reduced fault levels and maintain protection. So the third point is response to DG variability. DGs significantly change fault paths and current magnitudes. Conventional method assumes DGs always online, which is coordination errors. Adaptive system detects active DGs in real time, recomputes optimal relay settings, avoids over or under tripping. The fourth point is semi-adaptive limitations. Semi-adaptive adjusts based on predefined configurations but cannot track real-time DG status or fault changes, less flexible than full adaptive systems but still better than static conventional methods. Scenario 1, which is fault between buses 671 to 692. DGs active at buses 632, 633 and 675. Adaptive method outperformed conventional by reducing tripping time, example from 0.735 seconds to 0.68 seconds in grid connected mode, providing flexibility across all combinations of DG status and grid mode. Islanded mode showed biggest improvements using adaptive schemes versus fixed settings. Scenario 2, fault between buses 632 to 671. DGs at buses 633 and 692. Again, adaptive protection provided lower TMS and tripping times, especially in islanded mode, improved relay coordination, maintaining protection despite changes in DG operation or topology. Semi-adaptive helped, but still inferior to fully adaptive approach.
Hi, my name is Uday Kumar Satiselan, metric number 211090989. So I will proceed further with the results and discussion analysis. So for the scenario 3, it's about the multiple distributed generation units in grid connected mode. So for the overview, it's a configuration about multiple distribution connected DG units connected in grid connected mode. So what are the key features? The key features discussed here is the dynamic setting adjustments, adaptive protection scheme continuously resets relay setting based on the current distributed generation available and availability at that time, and also the output, followed by the real time distribution generation operation condition rather than assuming constant operation. So it's more feasible for any kind of situation, and it's also for the enhanced coordination, maintains a good coordination and fault selectivity across the entire section. So what are the benefits for it? Performance benefits are the more improved reliability, reduced risk, reduced false operation, and third is selective false clearance. Followed by scenario 4, it's about the islanded operation mode. For the islanded operation mode, there are two categories, which is semi-adaptive protection and also fully adaptive protection. So the semi-adaptive protections characteristics is aware of ice landing condition. Limitation is does not account for challenges in distributed generation availability, followed by the performance, which is better than conventional but still sub-optional relay settings. For the fully adaptive protection, it considers both ice landing detection and real-time DG availability. Followed by the capability, it dynamically adjusts relay parameters based on the current condition. And the performance-wise, it's more superior at fault isolation, which is more safe. And for the operating condition, the islanded operation mode system, it's actually it separates from the main grid, which is more secure. And also for the conventional protection, uses hard-coded relay settings. The limitations here is it attempts to identify ice landing, but open system oftentimes will cause miscoordination. So there's some limitation in terms of conventional protection compared to the operating condition, which is used in ice landing operating mode. And the last one, which is the multiple DG units connected. Here we can see it's done by the test configuration is done by fuel fault injection, multiple fault location throughout the network, and the DG positioning, different DG bus connection for each test. Variability, the test variation combinations of fault distance and active DG arrangements. For the adaptive mechanism, dynamic recalculation and pickup current adjustment, active DG consideration. And finally, for the performance objective, what is the advantage? It gives a fast clearance for the fault detection and also isolation. It's for selective operation and also for comprehensive coverage. So that's all from me. Thank you.